IP options. IP support a number of options that may be selected on a per datagram basis. Most of these options were introduced in RFC 0791 at the time IPv4 was being designed, when the internet was considerably smaller and when threats from malicious users were less of a concern. That's why IPv4 options are not commonly used today, because they were designed for the earliest version of the IP, which has smaller and the threats from malicious users were less of a concern. With IPv6, most of the options have been removed or altered and are not an integral part of the basic IPv6 header. Instead, they are placed after the IPv6 header in one or more extension headers. An IP router that reaches a datagram containing options is usually supposed to perform special processing on the datagram. In some cases, IPv6 routers process extension headers, but many headers are designed to be processed only by end host. In some routers, datagram with options or extensions are not forwarded as fast as ordinary datagrams. We briefly discussed the IPv4 options as background and then look at how IPv6 implements extension headers and options. So we start with discussing the IPv4 options, but take note, it is rarely used today. So table 5.4 shows most of the IPv4 options that have been standardized over the years. Options, if present, are carried in IPv4 packets immediately after the basic IPv4 header. Options are identified by an 8-bit option type field. This field is subdivided into 3 subfields: copy 1 bit, class 2 bits, and number 5 bits. Options 0 and 1 are a single byte long and most others are variable in length. Variable options consist of 1 byte type identifier, 1 byte of length, and the option itself. So here we have name, end list, number 0, value 0, length 1, description indicates no more options, etc. So this source routing is what we will discuss later. So it has a number 3 and 9, value 131 and 137, length is variable, description, sender list router waypoints for packet to traverse when forwarded. Loose means other routers can be included between waypoints. 3,131, strict means all waypoints have to be traversed exactly in order. 9,137. So it's rare, often filtered. So that will be important later in our IPv6 discussion. So again, it is supposed to perform special processing on the datagram, just like when it receives a router, a router receive an option or a packet from IPv4 with option, it must do something or a special action to process that. That's why it's slow. That's why it was not used as much today. Or usually the router that received those options, the router configured to reject those type of packets. In some cases, IPv6 routers process extension header, etc. The option area always ends on a 32-bit boundary. So it means it pad bytes with a value of 0 are added if necessary. So the options area, if not a 32-bit boundary, are padded by 0. This ensures that IPv4 header is always a multiple of 32 bits as required by the IHL field. So remember the IHL, it requires the 32-bit to have 0. The number column in table 5.4 is the number of the option. The value column indicates the number placed inside the option. Type field to indicate the presence of the option. Again, the value column indicates the number placed inside the option. So it's inside the option. Type field to indicate the presence of the option. These values from the two columns are not necessarily the same because the type field has additional structure. In particular, the first high-order bit indicates whether the option should be copied into fragments if the associated datagram is fragmented. Again, the first high-order bit indicates whether the option should be copied into fragments if the associated datagram is fragmented. The next 2-bit indicates the options class. Currently, all options in table 5.4 use option class 0 control except timestamp and traceroute, which are both class 2, debugging and measurement. Classes 1 and 3 are reserved. Most of the standardized options are rarely or never used in the internet today. Options such as source and record router, for example, require IPv4 addresses to be placed inside the IPv4 header. Because there's only limited space in the header, 60 bytes total, of which 20 are devoted to the basic IPv4 header, these options are not very useful today in today's IPv4 internet, where the number of router hops in average internet path is about 15. So because the average hop among routers is 15, these are not very useful today. In addition, the options are primarily for diagnostic purposes and make the construction of firewalls more cumbersome and risky. So it's for diagnostic purposes instead of a normal use, and the construction of firewalls because the construction of firewalls or it make the construction of firewalls more cumbersome and risky if you have a firewall in your network and simultaneously accepting options in your router. Thus, IPv4 options are typically disallowed or stripped at the perimeter of enterprise networks by firewalls. So thus, their use are usually rejected by firewalls. Within enterprise networks, where the average path length is smaller and protection from malicious users may be less of a concern, options can still be useful. So if the network is smaller, or you only have a small network and you don't care about malicious user, this option can be useful. In addition, the router alert options represent somewhat of an exception to the problems with the other option for use on the internet. Again, in addition, the router alert option represents somewhat of an exception to the problem with other option for use on the internet because it is designed primarily as a performance optimization and does not change fundamental router behavior. It is primitive more often than the other options. In addition, the router alert option represents somewhat of an exception to the problems with the other options for use on the internet Because it is designed primarily as a performance optimization and does not change fundamental router behavior, it is permitted more often than other options. As suggested previously, some router implementation have a highly optimized internal pathway for forwarding IP traffic containing the router alert options. Inform routers that a packet require processing beyond the conventional forwarding algorithm. So because this option requires a more careful configuration than a normal packet, so it does not concur with the normal forwarding algorithm. And they are also optimized, or some router implementation have a highly optimized internal pathway for forwarding IP traffic containing no options. IPv6 extension headers. In IPv6, special functions such as those provided by options in IPv4 can be enabled by adding extension header that follow the IPv6 header. Again, IPv6 extension headers. In IPv6, special functions such as those provided by options in IPv4 can be enabled by adding extension headers that follow the IPv6 header. So this extension header, unlike the option part of the IPv4, or the instead of it becoming part of IPv4 header, it actually outside of it, kind of like in the upper layer part. So it's just like a pointer. It used to point to the destination and the hop by hop receiver. We will discuss that later. The routing and timestamp functions from IPv4 are supported this way. So the routing and timestamp option are actually supported in IPv6 using this extension header, as well as some other functions such as fragmentation and extra large packet that were deemed to be rarely used for most IPv6 traffic. So this option in IPv6, or signifying that there is a large packet or a routing and a timestamp, actually makes the IPv6 more flexible, but still desired, and thereby did not justify allocating bits in the IPv6 header to support them. So sometimes you need to have a large packet, but again, the fragmentation are happening in the host. IPv6 do not allow that. So sometimes it's still needed. So IPv6 allow an extension header. Again, it's outside, so it has a fixed 40 bytes header. It's outside of it, so it was able to do it. With this arrangement, the IPv6 header is fixed at 40 bytes, and extension headers are added only when needed. In choosing the IPv6 header to be of a fixed size and requiring that extension headers be processed only by end host, again, extension headers be processed only by end host with one exception. The designers of IPv6 have made the design and construction of high-performance routers easier because the demands on packet processing at routers can be simpler than IPv4. So the demand for the router, unlike the IPv4, does not require a slowdown of packet or a change of algorithm or a change of management of the highly optimized forwarding IP. Is not as too costly when it comes to its processing, or it doesn't require the CPU or memory as much as it does with IPv4. In practice, packet processing performance is governed by many factors, including the complexity of the protocol, the capabilities of the hardware and software in the router, and traffic used. Extension headers, along with headers of higher layer protocols such as TCP or UDP, are chained together with the IPv6 header to form a cascade of headers. So here, along with the higher layer protocol like this IPv6 header, next header equals to TCP. We have 20 bytes. So as you can see, we still have 40 bytes here. But we can have a different pointing on the next hop. Like here, TCP. The next header it points is TCP. And here, the next pointer is a routing header. And here, routing header next header equals to fragment. Here, routing header next header equals to TCP. So IPv6 headers form a chain using the next header field. So this is the key, the next header field in extension headers. Headers in the chain may be IPv6 extension headers or transport headers. So it could be a transport header from its above, layer 3 to layer 4, or the actual configuration of IPv6 extension header, or different possible configuration. The IPv6 header appears at the beginning of the datagram and is always 40 bytes long. The next header field in each header indicates the type of the subsequent header, which could be an IPv6 extension header or some other type. Again, the next header field in each header indicates the type of the subsequent header. So this next header indicates the type that it is pointing to, such as here, routing header next header and routing header next header, which could be an IPv6 extension header or some other type. It could be TCP as well or from layer 4. The value 59, so it also provide that type or identifier using a value or a number. The value 59 indicates the end of the header chain. The possible values for the next header field are available at IP6 param, and most are provided in table 5.5. Where is that 5.5? So let's go back to that in the future video, but basically it has just like a table like this that has a value, number, etc. that signifies what type of header signifies that, whether it's TCP or extension header. So here we also have different extension headers that we can configure. So as we can see from table 5.5, the IPv6 extension header mechanism distinguishes some functions like routing and fragmentation from options. The order of the extension header is given as a recommendation, except for the location of the hop-by-hop options, which is mandatory. So an IPv6 implementation must be prepared to process extension headers in the order in which they are received. So again, IPv6 extension header mechanism distinguishes some functions like routing and fragmentation from options. So it has an options part which allows it to check whether it's for routing and fragmentation. The order of the extension given headers is given as recommendation, except for the location of the hop-by-hop options. So the order of this extension header is a recommendation for the router to help him on how it will process it, but the location of the hop-by-hop options which is a mandatory, meaning it must go to this router. So a hop by hop option is the next router it should point to, and the destination router should be fixed as well. So those are the only mandatory. Other than that, other than those two, all of this could process the extension header, the configuration based on what the receiving router processor. They can reject it, they can accept it, etc. based on their ideal way of receiving it. So an IPv6 implementation must be prepared to process extension headers in the order in which they are received. So an extension header, like an hop option, for an IPv6 network should be prepared to follow the hop, the next hop, and the final one. Now, there's actually two destinations that we will see in the table in the next video. There is a destination. The two destination option case happens when routing headers are present. So if there's a routing header, so it's not a TCP header, kind of like extension header for routing of IPv6. When an IPv6 packet includes a routing header, it's essentially saying this packet will visit several waypoints before reaching the final destination. That's why it has that header configuration. Now it will choose what's the next router it will send it to, and what's the final router. Think of it as IPv6 replacement for IPv4's loose source routing option, which you saw in the big table, which we discussed. The sender lists your router waypoints for packet to traverse when forwarded. Loose means other routers can be included between waypoints. So strict means all waypoints have to be traversed exactly in order. So that's what it is similar to, which you saw in which is almost never used today because of security concerns. In IPv6, the routing header contains a list of intermediate nodes. Example chain. IPv6 header, you have an argument next header to routing. So it means that the extension header it currently has in the next header is the routing. Now the routing header has a next header, kind of like an extension header as well, a destination option, which the final router it should traverse. Now you should follow this in order. The next router it should hop, and the final router, then destination option, then the TCP header, then it will get the TCP data. Each router listed in the routing header gets a turn to process and forward the datagram. So each router listed in the routing header, which this gets a turn to process and forward datagram. So it will follow that hop mandatorily, just like following the strict order of the router it should go to before it gets to the final destination. So why two destination options header exist? IPv6 designer realized something subtle. Different options may need to be interpreted by different destination. The first destination options header, position 3 in table 5.5, is for options meant for the next destination. So the position 3 or the first destination options in table 5.5, which we will discuss in the next video, is for options meant for the next header destination. I think we can actually see this. That's fine. So the second destination option, No, I don't have the copy of the table. So the second destination option header, position 8, so it's called position 8, is for options meant for the final destination, the end host. So in the table in the next video, we will actually see two position in one in this extension header, because it will tell you the next hop and the final destination. So the final destination is fixed. However, the reason why they have two position in one extension header is because the next hop could be different for different routers. So again, the second destination options header, position 8, is for options meant for the final destination, the end host. This allows routers or middle boxes that are part of the source route to see or act on some metadata. So the routers that will receive this will act on this IP or packet IP datagram metadata based on that extension header, while preserving the integrity of end-to-end data, since only the end host sees the second one. So the end host is the only one that can see that final destination header. All of the routers between it won't be able to see it. Now, connection to the IPv6 header chain and next header field. The next header field in the IPv6 base header and each extension tells you what follows. So for a packet using source routing, so again, the next header field in the IPv6 base header and each extension tells you what follows next. Like IPv6 header, the next header is equals to routing, then routing header, next header equals to destination options, next header equals to TCP header, TCP data. When the packet reaches the first waypoint, the IPv6 header's destination address field is temporarily set to that waypoint's IPv6 address. The kernel at that waypoint processes the first destination options header, then updates the IPv6 header to point to the next waypoint and forwards it. Only when the last waypoint is reached does the final destination options, position 8, get processed by the final receiver. Just a moment. Again, when the packet reaches the first waypoint, the IPv6 header's destination address field is temporarily set to that waypoint's IPv6 address. So this destination will be temporarily set to that waypoint IPv6 address or the next router waypoint's IPv6 address. The kernel at that waypoint process the first destination options header. Then updates the IPv6 header to point to the next waypoint and forwards it. So the kernel at that waypoint or that router will process the first destination option header it got from the like router 1, say. The router 2 or that waypoint will process the first destination option header, then updates the IPv6 header to point to the next waypoint and forwards it. Only when the last waypoint is reached does the final destination options, position 8, get processed. So this position 8 will only be processed by the true final receiver. So it maintains that end-to-end encryption. How this connects to an end-to-end checksum mathematics? Remember from before, the TCP checksum covers not only the TCP header plus data, but also a pseudo header including the source and destination IPv6 address from the IPv6 header. So a TCP checksum actually maintains the IPv6 integrity by having a TCP header plus data, but also the source and destination IPv6 address from the IPv6 header received. So what happens if the destination address field changes mid-route because of the routing header of this IPv6? The TCP checksum isn't recomputed at every hop. That would violate end-to-end integrity. Instead, the checksum is computed once by the sender using the final destination address, the position 8, the one that will appear in the IPv6 header after all routing headers are processed. So that position, it doesn't care about the position 3, it only cares about the final destination, which will prove that it actually routes to the true receiver. Intermediate routers temporarily rewrite the IPv6 header's destination address, but not the payload. The checksum still validates correctly when the packet finally reaches the end host. So an intermediate router can only temporarily change the position 3 but not the position 8. So it means that if it has the same position 8, that data or the payload or the TCP datagram is still the same. So the checksum still validates correctly when the packet finally reaches the end host, because the end host reconstructs the same pseudo header with its own final address. So again, the checksum still validates correctly when the packet finally reaches the end host, because the end host reconstructs the same pseudo header with its own final address. So it reconstructs, so it doesn't need a recomputation each router, because it reconstructs the same pseudo header of that IPv6 with its own final address, kind of like its final kernel. We're gonna now check if it's still a position 8, and it will compare to its header or the actual identity if it match. Now this is perfect example of how IPv6 extension header chain and the checksum group math coexist. The middle headers can mutate the envelope, the IPv6 header, but the end-to-end transport checksum and possibly security headers like AH or ESP guarantees that the payload integrity is not not broken. So at ESP and AH, or used for authentication, is actually done this way. The middle headers can mutate the envelope or the IPv6 header without changing the actual payload. So how this fits into the kernel forwarding logic we discussed in the previous video. IPv6 forwarding router, it checks what happens in the kernel. So the layer IPv6 forwarding router, what happens into the kernel, it checks IPv6 header, sees next header equals to routing, parses routing header, updates IPv6 destination address, decrements segment left, maybe process first destination options, So the first destination option is the next hop router, and it forwards packet. Transport layer and host. Only after all routing headers are processed does it receive the packet. Verifies checksum mat, TCP or UDP using the final destination address. So only after all routing extension headers are processed, so again we're talking about a routing extension header here, does it receive the packet. So after that routing identifier, what order it should hop in the network, after those traversed, does it get or receive the final data. Then verifies checksum mat or TCP or UDP using the final destination address. So it has a checksum. The way it does this checksum is comparing if that final destination 8 match its own identity. Now socket layer, user space, it get the clean, reassembled, verified TCP segment. In short, the two destination option rule is there to cleanly separate hop by hop metadata processed by intermediate nodes from end-to-end metadata processed only by the final receiver. And the ones complement checksum group properties are what make this entire chain address mutating process safe, because the checksum math ensures the payload remains valid despite temporary IPv6 header rewrites. So this checksum math that has this position 8 in its header or its end-to-end metadata is what makes it possible. Again, and the ones complement checksum group properties are what makes this entire chain's address process safe, because the checksum math ensures the payload remains valid despite temporary IPv6 header writes. Now the big picture so far, we've been exploring how traffic flows end-to-end through multiple layers. Layer 2, data link, Linux bridges, RSTP, MAC aging, concerned with where frames go on the local LAN. Layer 3, network, IP headers, routing, extension headers, concerned with where packets go globally. So this, the data or the Wi-Fi or the Ethernet are concerned in local, how it manage the local data or packets. Layer 4, transport, and layer 3 is concerned where packets go globally. Layer 4, transfer, TCP or UDP, ensuring data delivery between hosts. Layer 5 to 7, application. Protocol like LiveKit using DTLS plus SRTP to secure content. So the LiveKit or the video call app. So for example, this LiveKit that use WebRTC are actually those protocols are actually from the layer 5 to 7. Now this passage is about how IPv4 and IPv6 handle per packet control information, how routers and endpoints interpret options that can alter routing, timing, security, etc. So the timing, the routing, how fast it will go, will it be rejected? It doesn't pile per se the data in the application level. So these layers, layer 5 to 7 and 4, doesn't care about what happens in layer 3. It's just router talking to each other. Why IPv4 options existed? In IPv4, routers could inspect special option fields in the IP header to record the path, record route. So it could record the path it will take from router to router, hop to hop. But again, it was not being used today. It specified the route, source routing. It add timestamps where it when Did it arrive on that router carry security labels for classified networks, indicate special handling, router alert. But the IPv4 header is small, 20 bytes base, plus up to 40 bytes of options. Each option forces router to slow down and inspect the packet in software. So since it's using software, it must use a CPU and memory or allocate that to this type of packet. This became a scaling and security nightmare. Routers became smarter than they should be, and attackers could exploit this option. So they could use this option to, let's say you have a very important packet using this option, they can go ahead and pile that and get the data from it. So modern typical drop or strip packets with option. So modern routers typically drop or strip packets with options for safety and performance for IPv4. Now IPv6 redesign. It uses an extension headers. It means it outside of that base 40 byte size of its header. IPv6 designer wanted routers to be fast dump forwarders. Instead of this smart, the check option, it wanted a fast dump forwarder. So instead of cramming options into the base header, IPv6 introduced extension headers, a chain of headers that include optional information like this. Each IPv6 packet looks like this. IPv6 header, hop by hop options, routing, fragment, ESP. So these are the extension header that you could use for your packet, or depending on the type of data or fragment you want to send. You can send it, you can configure it via routing, fragment, how would you fragment it, ESP, etc. And you also have destination options. Now each header includes a next header field that tells the next one's type. So most importantly, only the hop by hop header must be processed by routers, not the destination option. All others are meant for end host only. Security, routing, so this is the routing timestamp, etc. So ESP, those are the timestamp, security, etc. This simplifies router design. Routers only read the first 40 bytes of each packet or the next router hop, and the rest is for endpoints. Connection to LiveKit, DTLS, and SRTP. Now connect this to your earlier question about LiveKit's end-to-end encryption. LiveKit, or this LiveKit, kind of like imagine it as a Zoom. We just want to know how does Zoom or real-time video conferencing actually work under the hood, or in TCP/IP terms. LiveKit media packets or audio or video travel over UDP or IP protocol. The payload RTP is encrypted using SRTP, and the key exchange uses DTLS. So that's where SRTP and DTLS in LiveKit came. And again, it's from 5 to 7. All this on top of IP. Meeting the security and confidentiality are handled above the network layer. So the confidentiality are handled kind of like TCP handling it for an IPv6 instead of having security make our checksum in IPv4. This application layer protocol, DTLS, SRTP, handles the security and confidentiality above the network layer or above the IP. In context, IPv6 and IPv4 headers are visible to routers. So these IPv6 headers are only IPv6 and IPv4 are only visible to routers. The actual data that is being sent to the user are still encrypted there. It is not visible to the routers, but encrypted content like SRTP payload is opaque, meaning they are encrypted in the upper layer. IP level options or extension headers don't affect the encryption. So this header that we're talking about, the IPv6 and IPv4, doesn't care or doesn't affect that SRTP. It's still confidential and ensure integrity up there. They're more about how packets move, not what they contain. So they're more about the header, whether it will follow the constrained hub-by-hub routers among the network or among these routers globally, or whether it doesn't care whether it goes here and there, as long as it is received by the end router fast. Kind of like this. This, for example, an IPv6 router will receive this type of application as an immediate or kind of like expedite forwarding, meaning it will prioritize this over other requests on its network or over other requests of the Wi-Fi on their network. So end-to-end confidentiality is verified by checking the DTLS handshake and SRTP encryption integrity, not IP headers. So IP options / header handle routing and control, while DTLS or SRTP ensures data confidentiality and authentication at higher levels. So again, the keyword is routing and control for IP. Not the confidentiality and authentication. Now connect to netlink, bridges, and forwarding. In your previous topic, or Linux Bridge BRCTL operates purely at layer 2, forwarding based on MAX. Netlink sockets are how the Linux kernel communication routing, bridging, and IP state to user space, like when IP routes change or RSTP port change state. So a netlink sockets, kind of like it's a vocabulary of Linux on how it communicates to routing. So it is a module for an IP or layer 3, it is a module for bridging for layer 2, and an IP state to user space. So it's also a module for a higher level layer, kind of like a module for all layers. Like when IP routes change or RSTP port change state, these netlink sockets handle that. When IPv4 or IPv6 options are present, Linux IP stack handles them via its own routing hooks, often in the kernel's net filter or IPv6 extension header handlers. So it uses their kernel's net filter or IPv6 extension header handlers. So that's what the router or receiving router does. So the change look like this: an app LiveKit DTLS or SRTP to transport UDP to network IPv6 header plus extension to data link bridge forwarding via netlink control to physical Ethernet or Wi-Fi. Each layer adds or removes its own headers. So each layer piles its own header to get the actual data and to know the source and destination address. And options or extensions at one layer don't break encapsulation or confidentiality at another. So just because it has options or more configuration in IP layer 3 doesn't mean it affected the actual datagram that the higher level will pile. Now why it matters today: IPv4 options are mostly dead, filtered. IPv6 extension headers are rare but still used. For example, IPsec. So the IPsec is actually the ESP and AH. We talk mobile IPv6, mobility header, router alert for multicast, fragmentation when needed. So mobile IPv6, mobility header, router alert for multicast fragmentation when needed. For example, when you run a LiveKit over IPv6, you may see extension headers for fragmentation or security payloads like ESP. So if your Wi-Fi support IPv6, we may see like an additional option in the header for fragmentation or security payloads, meaning that it is more secure because of the router configuration of that, or the router that sent it. if IPsec tunnels are involved or if IPsec tunnels are configured in their Wi-Fi. But otherwise, encrypted traffic stays end-to-end, unaffected by routing metadata. So the traffic, it's still the same. It's fast, unaffected by routing metadata. Now in summary, concept IPv4 options, layer L3. So a concept, an IPv4 options, it's in layer 3. Function, routing, timestamps, labels, still use, rare, filtered, IPv6 extension headers, layer 3, L3, function, modular routing or control. So if you want to control how it routes, if you want to make it secure, etc. So this is how you configure it. For example, your UDP or LiveKit, this is how you configure it to be more secure. If you want to present your thesis as a more secure, you can implement an IP header option such as ESP or IPsec and for IPsec, ESP and AH for IPsec. DTLS or SRTP, that's in layer 4 to 7. Function end-to-end encryption, still use, yes, for LiveKit and WebRTC. Concept, netlink, layer, kernel user interface. So it's a kernel to user interface. It's how kind of like tapping into the OS. Function, manage bridges. The layer 2, it manage routing. The layer 3, still use, yes, Linux only. Bridges, RSTP, layer 2, function, frame forwarding. Still used, yes, for LAN switching or for local area network. Now the IPv6 header chain equal the structural container for upper level layer protocols. In IPv4, the protocol field 8 bits inside the IP header simply says what comes next. Like number 6 equals TCP, 7 equals UDP. IPv6 generalizes this idea. It introduces extension headers, each one linked to the next by the next header field. So each one linked to the next by next header field. Kind of like it knows what it is next to, but not the final destination. Now IPv6 header, next header equals routing. Routing header, next header equals to fragment. Fragment header, next header equals TCP. TCP header to TCP payload. Each header hands off parsing to the next. So the header of each one hands off the parsing, like kind of like telling, hey, your router, here's the packet. It's up to you how you will parse it, right? So exactly like a linked list in memory. The chain replaces the old IPv4 options area, which sat inside the base header and caused complexity. So instead of putting that inside the information inside the base header, and instead of adding complexity, it provide the option to the next router. On next header, it will send to. IPv6 instead modularizes options into separate extension headers. So that's how it modularizes. It provides flexibility because it provides the header or the option into a separate extension header. The checksum mat sit inside the last protocol in that chain, TCP or UDP. Remember our earlier deep dive on the internet checksum? The 16-bit ones complement some, forming an abelian group. The mat is not part of IPv6 base header. IPv6 itself removed the IP level checksum. Instead, it is still used by TCP, UDP, and ICMPv6, which sit after the IPv6 header in the chain. So in your diagram, IPv6 header, 2 extension headers, the TCP header include checksum field. So again, the mat in the checksum is not part of the header of IPv6, unlike in IPv4. However, TCP and UDP and ICMPv6 still sit after the IPv6 header in the chain. So IPv6 header, we have extension header, then TCP header, which the TCP header are the one that includes the checksum field. When the kernel constructs the datagram, it runs the group base one's complement addition over the TCP header plus data. So the kernel of the routing or the router is responsible for doing this. A pseudo header derived from the IPv6 header, source or destination addresses, etc. So it runs group base one's complement addition over the TCP header plus data and the pseudo header it received as a source and destination address header from the actual IPv6. The checksum mat guarantees end-to-end integrity across layers, even though the router chain, hop by hop, routing, etc. may insert or remove headers in between. So they can remove the headers in between routers, but these are guarantees by TCP or the Linux in the receiving router or the final router. That's how your abstract algebra discussion connects to the group properties of the checksum operation. Let this layered chaining system detect corruption end-to-end no matter how many extension headers are present. So no matter how many extension header goes into that routing, it doesn't care. It still receives the same datagram, TCP datagram. How this ties to the kernel data path we diagrammed earlier. When a packet is sent, step 1, kernel layer, socket or transport layer, TCP or UDP, what happens? It builds header, compute checksum, group mat, attaches data. Step 2, kernel layer, IPv6, add base IPv6 header, set next header, quote TCP or first extension. Step 3, kernel layer, optional extension layer. What happens? Adds hop by hop, routing or fragment headers, chaining via the next header field. Step 4, kernel layer NIC driver. What happens? It pushes it to hardware. Hardware computes Ethernet CRC, different checksum. Step 5, kernel layer receiving host. What happens? It passes chain in reverse. Verify checksum mathematically. So the ones complement abelian group logic ensures that no matter what optional headers sit in the middle, the receiver transfer layer can mathematically confirm the original's payload integrity. Why this modular design matters? IPv6 versus IPv4. IPv4 mixed routing options and end-to-end data into one header. Slower, more complex router code because the router needs to parse that a mix inside this header. IPv6 separate concerns. Routers only read the base 40-byte header, fast path, and host handle everything beyond the routing, fragment, ESP. So beyond this routing on how It will move between router to router. The end host handle everything. So the router between them will decide how it will handle the routing, whether it will reject it, accept it, how fast it is, etc. This aligns perfectly with the end-to-end principle we discussed before. Router forward efficiently, and host enforce integrity and correctness, checksum, group logic, encryption, etc.